Friends, in this video, we shall try to understand the idea or concept of reduced mass. In the year 1864, James Clerk Maxwell understood that electricity, magnetism, and light are related to one another. He mathematically proved that light is an electromagnetic wave. By the way, what is a wave? Without going into the formal definition of a wave, we can understand that in a wave, energy is transferred from one point in space to another point in space. And you are familiar with different kinds of waves like water waves, sound waves, etc. And the kind of energy transferred in water waves or sound waves is mechanical energy, that is kinetic energy plus potential energy. And to transfer mechanical energy from one point to another point in space, we need a medium or matter. Without a medium, mechanical energy cannot be transferred from one point to another point. That is why these waves are called mechanical waves. So a mechanical wave is a phenomenon in which mechanical energy is transferred from one point to another point in space. Similarly, electromagnetic wave also transfers energy from one point to another point in space. But the kind of energy transferred by electromagnetic wave is not mechanical energy. It is a different kind of energy called electromagnetic energy. And the interesting thing is, to transfer electromagnetic energy from one point to another point, we do not need a medium. So electromagnetic wave is a phenomenon in which electromagnetic energy travels from one point to another point in space without needing a medium. And that is why we say electromagnetic wave is self-propagating. That is, it is a phenomenon in which electromagnetic energy somehow travels from one point to another point even in the absence of a medium. And during the process of evolution, we developed some sense organs that can detect certain kinds of electromagnetic energy. For example, our eyes. When a kind of electromagnetic energy enters our eyes, some activity is produced in a part of our brain called visual cortex. And this activity produces an experience that we call seeing. And the electromagnetic energy that creates this experience of seeing is what we call visual light. And the other sense organ that can detect light or electromagnetic energy is our skin. But skin cannot detect visible light that our eyes can detect. Skin can detect a slightly different kind of light or electromagnetic energy that is for some reason called infrared light. And when infrared light falls on our skin, the experience or the sensation caused is called heat. So the heat you feel when you stand near a fire is mostly because of the infrared light emitted by the fire hitting your skin. Also, the heat you feel in sunlight is because of the infrared rays or the infrared light present in sunlight. Now the question is, what is the difference between visible light that our eyes can detect and infrared light that our skin can detect? Moreover, within visible light, there are lights of many different colors. That is our common experience. When you look at a particular visible light, it may appear red to you. And some other visible light might appear green, yet another visible light might appear blue. So now the question is, what is the difference between these lights of different colors and infrared light and so on? See, all of them carry electromagnetic energy. So all of them are electromagnetic waves. Then what is the difference between them? Why one light appears green and another light appears blue? What is the difference between lights of different colors and infrared light, etc.? Now look at this picture. In this picture, there are two waves, one drawn in blue color and the other one in red color. Obviously, these two waves are not identical. There is some difference between these two waves. And if I ask you to describe that difference, how do you do that? Now, one of you may say that the red wave is bigger and the blue wave is smaller. And someone else might say that the red wave is kind of stretched out and the blue wave is rather compressed. But this is not the right kind of vocabulary to describe the difference between these two waves. So, to differentiate these two waves, we need to look for or define some properties that can uniquely identify a wave. And one such property is called wavelength. Now, wavelength is the distance covered by one crest and one trough. This is a transverse wave and this is a crest and this is a trough. And the distance covered by one crest and one trough is called one wavelength. Now what is the wavelength of this blue wave? Again, it is the distance covered by one crest and one trough, right? So this is the wavelength of the blue wave. And obviously, the wavelength of the blue wave is much smaller than the wavelength of the red wave. So now we developed some vocabulary to describe the differences between these two waves. We can simply say that these two waves have different wavelengths. And the symbol for this property of wave is lambda. Wavelength is represented by this symbol. Now, in addition to visible light and infrared light, we also discovered other kinds of light like ultraviolet light, X-rays, gamma rays, microwaves, radio waves. All these are electromagnetic waves. That is, they all carry electromagnetic energy from one point to another point. Then what is the difference between these kinds of light? We are able to see some light and our skin is able to sense some light. But we are neither able to see nor sense any of these other kinds of light. So obviously there must be some difference between these kinds of lights. So what is the difference between them? We can understand the difference between these different kinds of light with the help of this property called wavelength. The simple answer is, though all of them are electromagnetic waves, they have different wavelengths, like shown here. Out of all these electromagnetic waves, gamma rays have the shortest waves, whereas a single radio wave could stretch over many kilometers. So as we go from gamma rays to radio waves, the wavelength increases. So electromagnetic waves come in different sizes, that is, with different wavelengths. So using this property wavelength, we are able to differentiate different electromagnetic waves. Though wavelength is a very convenient property, for our present discussion, the reciprocal of wavelength is even more convenient. And the reciprocal of wavelength is defined as wave number. And its symbol is nu with a bar on the top. So nu bar is the reciprocal of wavelength and its unit is per centimeter. Now what does wave number represent? It tells the number of waves that fit in a length of 1 centimeter. So wave number gives the number of waves per 1 centimeter length. So here is one wave, this is 2, 3, 4, 5 and 6. So here in 1 centimeter there are 6 waves. So wave number here is 6 per centimeter. It is as simple as that. Wave number is the reciprocal of wavelength and it tells the number of waves that fit in a length of 1 centimeter. Now, many of us are familiar with discharge tube experiments. We studied these experiments in lower grades. In a discharge tube experiment, we take a glass tube that is called discharge tube, fill it with a gas at low pressure and pass electricity through it. As simple as that. When electricity is passed through a gas at low pressure, it begins to glow with a particular color. That means it starts emitting light or electromagnetic energy. And the color of the glow depends on the gas the discharge tube is filled with. If this tube is filled with hydrogen gas, it glows with pinkish red color. If it is filled with neon gas, it glows with a different color. Now let us take the case of hydrogen gas. When this tube is filled with hydrogen gas, it glows with a single pinkish red color. And based on this, we would assume that all the electromagnetic waves emitted by this hydrogen gas have the same wavelength. That is because every electromagnetic wave within the visible light has a particular color. Every time you look at an electromagnetic wave of a particular wavelength, your mind sees the same exact color. So one wavelength means one color. And it is natural to assume that the converse is also true. That is, if you see one color, that means one wavelength. So because we are seeing only one color in this glow, it is natural to assume that all the electromagnetic waves coming out of this discharge tube have the same wavelength. But is this assumption correct? Let us see. To understand if the light emitted by this hydrogen gas consists of electromagnetic waves of a single wavelength, or if it is a mixture of electromagnetic waves of different wavelengths, we can take the help of a prism. Prism has an ability to bend electromagnetic waves with different wavelengths by different angles. So if you pass the light emitted by this hydrogen gas through this prism and collect the light coming out of the prism on a screen or a photographic plate, you can clearly see the various colors or the various wavelengths that are present in the light emitted by this gas. This is called dispersion of light. So, a prism can separate electromagnetic waves of different wavelengths and clearly show them to us. When Balmer collected the light coming out of this prism on a photographic plate, he noticed a series of lines that we call Balmer series. And each line in this series corresponds to light of a particular wavelength emitted by this hydrogen gas. So by looking at this series of lines, we can easily understand that this hydrogen gas is in fact emitting a mixture of electromagnetic waves with different wavelengths. Then, why does this mixture appear to have a single color when I look at it? That is because when a mixture of colors enter our eye is incapable of differentiating various colors present in that mixture. Instead, it makes up a fake color in our mind. That is why this mixture appears to have a single color, though it consists of different colors. So it is a limitation of our eye. Therefore, when it comes to figuring out the various colors present in a mixture of colors, don't trust your eye. Instead, take the help of a prism or a grating to figure out the various colors present in the mixture of light. Now, most of the lines present in the Balmer series correspond to wavelengths in the visible light. That is why we say Balmer series is in visible region. A few years later, Lyman discovered another series in the ultraviolet region, and later on, many different series were discovered in the infrared region, namely Passion, Brackett, Fund, Humphrey, and so on. Here I have shown only the Passion series present in the infrared region and omitted the others. So from this we understand that this hydrogen gas is not only emitting visible light, but it is also emitting some ultraviolet light and infrared light. And a series of wavelengths of various electromagnetic waves emitted or absorbed by a substance is known as spectrum. Now in this picture, instead of showing wavelengths, I am showing wave numbers, that is reciprocal of wavelength, because that is more convenient for our present discussion. So what we have here is a series of wave numbers of various electromagnetic waves emitted by this hydrogen gas. So this is a spectrum. And because these are the wavelengths of electromagnetic waves emitted by a substance, it is called emission spectrum. And because in this spectrum we have separate discrete lines, it is called line spectrum. So this is emission line spectrum of what? Of hydrogen gas. See, under normal conditions, hydrogen gas consists of hydrogen molecules. In each hydrogen molecule there are 2 hydrogen atoms. But during electric discharge, hydrogen molecules first split into separate hydrogen atoms. And it is these hydrogen atoms that are actually emitting these electromagnetic waves. So this line spectrum that we have shown here is emitted by hydrogen atoms, not hydrogen molecules. So here we have the emission line spectrum of hydrogen atoms. Now what are we seeing in this picture? A number of lines. Even these white blocks that appear continuous are not actually continuous. They are also a series of separate distinct lines. But the spacing between these lines is so close that it is not visible to us. That is why these separate lines are appearing like a block. So understand that everything in this picture is a line. Separate, distinct line. And a fancy word for separate and distinct is discrete. So in this picture we have a number of discrete lines. Discrete means separate and distinct. And each line corresponds to a particular wavelength of light emitted by this hydrogen gas. Now look at these wave numbers. Do you see any pattern or relationship between these numbers? No, right? They appear pretty random. So based on these numbers, one would naturally think that hydrogen atoms are emitting electromagnetic waves of some random wavelengths. Or the emission of electromagnetic energy by hydrogen atoms is a random process, because there appears no pattern or relationship between these numbers. So what do you expect to see when you produce the line spectrum of hydrogen atoms a second time? Naturally, we expect to see a different line spectrum, because these numbers are giving me an impression that the emission of electromagnetic waves by hydrogen atoms is a random process. But to our surprise, you may produce the line spectrum of hydrogen atoms a million times, you will get the same exact line spectrum. Isn't that amazing? So that means it is impossible to make hydrogen atoms produce an electromagnetic wave with a wave number that is between these two values. Whether the hydrogen atoms are produced in your laboratory, or whether these hydrogen atoms are present in the distant star that you see in the night sky. So all hydrogen atoms in the entire universe produce the same exact identical line spectrum with absolutely no differences. And the story gets even more interesting when we replace this hydrogen gas with some sodium vapor. Sodium vapor consists of sodium atoms, and sodium atoms also produce a line spectrum, but the line spectrum produced by sodium atoms looks entirely different from the line spectrum of hydrogen atoms. Similarly, atoms of mercury also produce a line spectrum that looks different from the line spectra of atoms of all other elements. So atoms of all elements produce line spectra, but they all look different. Or atoms of no two elements produce the same line spectrum. And this is amazing. The unique and same line spectrum produced by atoms of a given element is trying to reveal a deep secret of nature if we have the ability to see it. It is trying to tell us that the emission of electromagnetic energy by these atoms is, after all, not a random process. there is some pattern or order to the emission of electromagnetic energy by these atoms. That is why we are getting the same exact line spectrum from the atoms of a given element. And Bohr and Rydberg tried to find a pattern between the wave numbers found in the line spectrum of hydrogen atoms purely by trial and error. And they finally found this formula for the wave numbers present in the hydrogen spectrum. It is given by capital R times 1 by n1 square minus 1 by n2 square, where n1 and n2 are positive whole numbers and n2 is always greater than n1. And you know, to get the wave numbers found in the Lyman series, you have to use a value of 1 for n1, and obviously n2 is greater than n1, so n2 must be greater than 1. So if you use the value 2 for n2, you will get one spectral line, and to get a different spectral line, you have to use a different value of n2. Similarly, for the Bohr series, n1 is equal to 2 and n2 is any whole number greater than 2. By using different values for n2, you will get the wave numbers of different spectral lines in the Bohr series, and so on. And here capital R is called Rydberg's constant, and its value is found to be 109678 per centimeter from the wave numbers found in the hydrogen spectrum. So this is the experimentally measured value of Rydberg's constant, because we obtained it from the wave numbers of these spectral lines. And even after Rydberg found this empirical formula by trial and error, for the wave numbers of the electromagnetic waves emitted by hydrogen atoms, that is, for the spectral lines of hydrogen atoms, the questions pretty much remain the same. Why hydrogen atoms obey this formula during the emission of electromagnetic waves? Or in other words, why hydrogen atoms emit electromagnetic waves with these discrete wavelengths and nothing else? Why it is impossible to obtain an electromagnetic wave with a wave number of our choice? It is impossible to obtain this electromagnetic wave or electromagnetic wave that corresponds to this wave number from hydrogen atoms. And these are not easy questions to answer. And classical physics failed to explain the line spectra of atoms, an apparently simple phenomenon. All we have done here is took some hydrogen gas and passed electricity through it and analyzed the light emitted by these hydrogen atoms. And classical physics could not explain this. And to explain the spectral lines of hydrogen atom, for the first time in the year 1912, a Danish physicist by name Neils Bohr came up with a radical new theory that is based on Planck's quantum theory. And using the postulates of his theory, Neils Bohr was able to explain the prominent spectral lines of the hydrogen atom. And he was also able to derive the formula that Rydberg found by trial and error. Now, Neils Bohr's model of atom is not the goal of this video. We shall discuss that in a separate video. But understand that using the postulates of his theory, for the very first time, Neils Bohr was able to theoretically derive an expression for Rydberg's constant in terms of mass of the electron, charge on the electron, speed of light, and Planck's constant. And don't get scared by this expression. You don't have to memorize it. But we can calculate theoretically the value of Rydberg's constant by substituting the values for these physical quantities and Planck's constant. And when Niels Bohr theoretically calculated the value of Rydberg's constant by using this expression, he obtained a value of 109,737 per centimeter. And as we previously discussed, the experimentally measured value of Rydberg's constant is 109,678 per centimeter. See how astonishingly close this theoretically calculated value to the experimentally measured value of Rydberg's constant. This itself is a huge success for Bohr's model of atom. Though the calculated and the experimentally measured values of Rydberg constant are very close to one another, the calculated value is slightly bigger than the measured value. And Niels Bohr wondered why the calculated value is slightly bigger. And he found a mistake in his calculations. We all know that according to Niels Bohr, the electron in the hydrogen atom revolves around the nucleus, that is the proton, in some fixed circular orbits. And let us say this electron is revolving around the proton in the first orbit. And if we assume that this electron does not have any velocity, then due to electrostatic attractive forces, this electron would collapse into the proton. See, electron has a unit negative charge and proton has a unit positive charge, and opposite charges attract each other. So this electron must have some tangential velocity. Otherwise, there would be no hydrogen atom because the electron would collapse into the proton. Let us say this electron has a tangential velocity of v. Now, if this electron has a tangential velocity, then it must continue to move in a straight line and gradually move away from this proton or the nucleus, right? That is Newton's first law. A body in constant motion must continue to move in a straight line. But this electron, instead of going away from the nucleus, it is revolving around this nucleus. Why? Though this electron is moving with a tangential velocity, this positively charged proton exerts a coulombic attractive force on this negatively charged electron. And the magnitude of that attractive force is given by Coulomb's law, a constant k times the product of their charges over square of the distance between them. So this proton constantly exerts a pull on this electron because of this coulombic attractive force. And because of that reason, instead of going away from the proton, the electron maintains a circular motion around this proton. And if there is a force acting on a body, then it must accelerate. That is Newton's second law, F is equal to ma. If me is the mass of the electron and F is this coulombic attractive force exerted by the proton on the electron, then it must produce an acceleration that we are calling AE. So F is equal to me times AE. Then AE is equal to F over me, right? And this acceleration is what is called centripetal acceleration or center seeking acceleration. Because of this coulombic attractive force, this electron is seeking to approach the center of this circular orbit. And this force is what is called centripetal force. So it is because of this centripetal force that this electron is keeping a circular path around this proton. And so far we touched Newton's first law and Newton's second law. Then what about Newton's third law? That says for every action there is an equal and opposite reaction. If the force exerted by this proton on this electron is action, then what is the reaction? Can you think about it? Simple. If this positively charged proton exerts an electrostatic attractive force on this negatively charged electron, then this negatively charged electron does the same. It also exerts a coulombic attractive force on this positively charged proton. And if one is action, the other one is reaction. If the force exerted by the proton on the electron is action, then the force exerted by the electron on the proton is reaction, and they are equal in magnitude but opposite in direction. So that means there is a force acting on this positively charged proton. And if there is force, there must be acceleration. If mp is the mass of the proton and ap is its acceleration due to this force, then F is equal to mp times ap, or mp is equal to F over ap. But Niels Bohr initially assumed that this proton is at rest even though there is this force acting on it. That means he assumed that the acceleration of the proton is zero despite this force acting on the proton. Now, if the acceleration is zero, that is in the denominator, then what will be the mass of the proton? Infinity, right? So, in other words, he assumed that the mass of this proton is infinite. That is why sometimes we put a subscript infinity to this r in this expression for Rydberg's constant to indicate that this is the expression for Rydberg's constant, assuming that the mass of the proton is infinite. And it is because of this wrong assumption that the calculated value of Rydberg's constant is slightly bigger than what it should be. Then to correct it, what should we do? Simple. We have to take into account the fact that the proton is also accelerating because of the force exerted by the electron on it. So, in the hydrogen atom, both the proton and the electron are revolving, not just the electron. But they are revolving around what? They are revolving around their common center of mass. In this video, we don't have to spend a lot of time discussing the concept of center of mass, but understand that both the proton and electron are revolving around their common center of mass in the hydrogen atom according to Niels Bohr's model of atom. And if capital F is the force exerted by the proton on this electron, and me is the mass of the electron, and ae is the acceleration induced by this force in this electron, then according to Newton's second law, F is equal to me times ae, or ae is equal to F over me. Then what about the proton? See, the electron exerts an equal amount of force on the proton as well, but in the opposite direction. So, to indicate that it is in the opposite direction, we have a negative sign here. So, minus F is equal to, let us say mp is the mass of the proton and ap is the acceleration induced by this force in this proton. Again, by Newton's second law, minus F is equal to mp times ap, then ap will be equal to minus F over mp. So this is the acceleration of the electron and this is the acceleration of the proton. Then what is the relative acceleration between these two particles? Relative acceleration is given by the difference between their individual accelerations, ae minus ap. and AE is equal to F over ME minus of, and AP is equal to minus F over MP. So minus of minus F over MP. And if you take out F, we will have F times 1 over ME plus 1 over MP. So this is the relative acceleration between the electron and the proton in the hydrogen atom. And this is the correct representation of the hydrogen atom according to Neils Bohr's theory. But I have a problem with this, though it is correct. It is complex. See here, both proton and electron are revolving around their common center of mass. So then there is one radius for the orbit of the proton, another radius for the orbit of electron. To tell the position of the proton in the three-dimensional coordinate system, we need 3 xyz coordinates. To tell the position of proton, another 3 coordinates for the position of electron. You have one acceleration for the electron, one acceleration for the proton, and so on. So calculations involving such a system are complex, though this representation is correct. Then what should we do? See, our life was much easier when only the electron was revolving around the proton and the proton was at rest at the center of the atom. So again, our life becomes easier if we somehow convert this system in which both proton and electron are revolving around their common center of mass into a system in which only the electron is moving and the proton is at rest. So two particle systems in which both are moving are complex. So to make our lives easier, we try to create a fake model in which only one particle is moving and the other particle is at rest. This is only for our convenience. There is no law of physics that mandates you to do this. And if you are happy with this two particle system in which both are moving, more power to you. Use it. But most of us find it difficult. That is why we come up with this fake model that is much simpler to study. Now, to make this simpler fake model from the real model, we impose two conditions. The first condition is that the proton must be at rest at the center of the atom, and it is only the electron that goes around the proton. That means we are again assuming that the mass of the proton is infinity. That is one difference between the real model and the fake model. And we keep the rest of the properties same. The charges on the proton and electron are same in both these models, and the distance between them is also same. That means the force exerted by the proton on this electron is also same in both these cases, because it is given by k times the product of their charges over square of the distance between them. So the magnitudes of the charges are same in both these models, and the distance between them is also same. Therefore, the force exerted by this electron in this fake model is also F. Now, what is the second condition? The second condition is that the perspective or the experience of the electron must be same in both these models. We cannot change that. That means if you imagine you are sitting on this electron in the real model, the relative acceleration that you experience is this, that is AE minus AP. Even in this fake model, the electron must experience the same amount of relative acceleration. But in this fake model, we are assuming that the proton is at rest, that is, its acceleration is 0. Then, how can this electron experience the same amount of relative acceleration as in the real case if we are not allowing the proton to accelerate? See, in the real model in which both the electron and proton are accelerating, the electron contributes some amount of acceleration to the relative acceleration and the proton contributes some. But in this fake model, we are not allowing the proton to accelerate. AP is equal to 0 and it is only the electron that is accelerating. Yet we want the same amount of relative acceleration in both these models. How do we achieve this? The only solution here is we must put additional burden on this electron. We must ask the electron to contribute the amount of acceleration that was contributed by the proton in the real model, in addition to its own contribution to the relative acceleration. So we must ask the electron to take the burden of this proton also. Now, how can this electron have more acceleration? F is equal to ma, right? So if you want more acceleration, you have to apply more force. But remember, the force experienced by this electron is same in both these models. This is coulombic attractive force that depends only on the magnitudes of these charges and the distance between them. They are same in both these models, so the force is same in both these models on this electron. Yet, we want the electron to accelerate more. How is that possible? If you want more acceleration for the same force, the only way out is to reduce the mass, right? So, if you want this electron to have more acceleration, because the force is same in both these cases, you have to assume that the mass of the electron in this system or in this model is less than the real mass of the electron. That is why this assumed or imaginary mass of this electron is called reduced mass, because it is less than the real mass. Now let us derive an expression for the reduced mass of this electron in terms of the real mass of the electron and proton. The symbol for reduced mass is mu, mu. Now let us say the acceleration of this electron in this fake model is AE prime and the acceleration of the proton is AP prime. Then what is the relative acceleration between these two in this fake model? Let us call this A prime relative, that is equal to AE prime minus AP prime. And we are not allowing the proton to accelerate, so AP prime is equal to 0, then it becomes AE prime. So it is only the electron that contributes entirely to this relative acceleration. And as we just discussed, the relative acceleration in the fake model and in the real model must be same. That is A prime relative is equal to A relative. And A prime relative is nothing but AE prime. AE prime is equal to A relative, that is equal to F times 1 over ME plus 1 over MP. And if mu is the mass of this electron and AE prime is its acceleration and F is the force acting on it, according to Newton's second law, F is equal to mu times AE prime, or AE prime is equal to F over mu. Now look at these two equations. Their left hand sides are the same, so we can equate their right hand sides. So F over mu is equal to F times 1 over ME plus 1 over MP. We can cancel these two out and we will be left with 1 over mu is equal to 1 over ME plus 1 over MP, or mu is equal to ME times MP over ME plus MP upon simplification. Now finally, where did Niels Bohr go wrong? In both the wrong model that he initially used and in the fake model that we just created, we are assuming that the proton is at rest without any acceleration, or we are assuming that its mass is infinity. Then what is wrong with this model? See, if you assume that the mass of the proton is infinity or it is at rest, then you must also assume that the mass of the electron is slightly less than its actual value. So you have to use the reduced mass of the electron and not the real mass of the electron. That is what was wrong with his initial calculations. See, in this expression, he is using the actual mass of the electron, which is slightly more than the reduced mass. That is why the value of the Rydberg's constant, or the calculated value, is bigger than or slightly bigger than the measured value. Now what should we do to correct this expression? We have to replace me with the reduced mass of the electron. So this is the correct expression for the Rydberg's constant, and it is denoted by capital R with the subscript capital H. And if you calculate the value of Rydberg's constant using reduced mass, then the calculated value will be pretty close to the experimentally measured value. And in case you did not realize, this is a spectacular success of Neils Bohr's model of atom.